Okay, so let's just have a look at what we have seen last week. So now we are studying games which are called transferable utility games, or TU games. These are games where players can form or can be in a coalition. A coalition is a subset of n, of the set of n players, and it's transferable in the sense that the money or the utility get by one coalition can be distributed among the coalition. So it means these games are described by the set of n players and a function v, which is defined on, this is the set of all subset of n, so all possible coalitions. So it takes a coalition and it sends to a real number, and we call whenever you apply this to a coalition, so V of S is the worth of a coalition, the utility that one coalition can get. And I just define a few additional properties for this game: the notion of super additive TU game, the notion of weakly super additive TU game, additive or monotonic, or zero normalized. I gave the definition for these notions. And then there is a question: how do you distribute the utility, or how do you allocate the utility between the players? So it means the way to allocate it is, in fact, to define a value in Rn, and each entry of this vector is what one player will get. So player I will get the value x index I. And we want first to define a suitable subset of all possible allocations. So the first definition was a set of imputations. It's a set of points in Rn such that the sum of all utilities that the n players, this is a n, that the n players get is equal to the total allocation for this game, or the worth of the grand coalition for this game. This was a set of imputation. So we have this condition and the condition that each player should get more than if he's playing just by himself without interacting with the other one. So this is a set of imputations. These are the first two conditions. However, this set is too big because one coalition might decide not to take a certain value in this set. So you should think about Rn, and this is I of V, the set of imputation. But for example, some coalition might not be interested in a certain value or a certain point because it's not very interesting for them. So we define the more important subset, which is the Kerr. So it's a set of points in the set of imputations, but such that the sum for each coalition, the sum of the different contributions inside the coalition is bigger than the worth of the coalition. So it's a stronger requirement compared to the previous one, the set of imputations. But it means for, let's say, suppose that this is a Kerr, so this is only this part. Then if you take a point in this part, in the Kerr, no coalition has interest of not choosing a point here because it's better for any coalition. So it means no coalition will complain about the point here. However, you still don't know which one to choose on according to which rule. So there was a description of the Kerr. The Kerr is very important, but it doesn't solve the problem because it doesn't tell you how to choose a point in this set. Or this set might be empty. This is also true. So it might be that there is no good way to divide or to allocate the utility such that all coalitions are happy. Then we try to give a second characterization of points here. So I introduce the notion of domination through a coalition, or this notion of domination and undominated. And once we have these three notions, we were able to characterize points in the Kerr. So the points in the Kerr are all undominated. This is a property they have. And in addition, if the game is super additive, the Kerr contains all undominated elements of the set of imputation. So it means they have an additional property than just being in the Kerr. And I just mentioned some properties of these two sets. The set of imputation and the Kerr, they are bounded convex polytopes. And I didn't give the precise definition, but you can easily figure out what it is, or you just look at some pictures. It's a subset of Rn with all faces made by planes, hyperplanes. So this is a polytope. And I also introduced a very specific class of games, which are called simple games, where this function takes only the value 0 or 1, only two possibilities. And in this setting, we introduce the notion of a veto player. And we had a more specific description of the Kerr for these games. And I asked if somebody wanted to better understand the description of the Kerr to write a report on this. It's not difficult, but it would be good to have a better understanding with an example. And the last thing I introduced, it's just a little bit more advanced, but as I said, sometimes the Kerr is empty. So if the Kerr is empty, it means there is no point that all coalition would accept. And I gave a if and only if condition for a non-empty Kerr. So for this, I had to introduce the notion of restriction of a game to a subset, the notion of balanced family of coalitions, which is it should remind you the notion of mixed states. Then what is a balanced TU game based on this? And then there is an equivalence between balanced TU games and non-empty Kerr. But it's just a little bit more advanced. But it's good to know that there is a characterization of non-empty Kerr. Okay. So that's what we have seen last week. And today we are going to work essentially on this question, how to distribute allocations between players. So how can we decide how to distribute the money or the utilities among players? Because we haven't seen any rule so far. So today we will see 3 and 4, and these rules have to respect some conditions. If you have any question, of course, you interrupt me at any point. So the first thing we are going to look at is what is called the, I guess, the Shapley value, or I don't know how to use this name, Shapley value. It's going to be one allocation, so one set of rules for giving or for distributing the utility. Okay. And in fact, in the recorded lecture, we did something similar for bargaining problems, so it should remind you something. So I just recall for TU game, for these transferable utility games, an allocation rule is a map or function. I use map because it's shorter, is a map phi from the set Gn to Rn. So what is Gn? Gn, I remind that this is a set of all TU games. So we would like to have one function which take any TU game and send it to one point. And this point is a way we distribute the allocations, or we distribute the utility or the money. So this is what we are looking for. And this phi, of course, has to respect some condition that we are going to state. So in order, and precisely the Shapley value is one such rule. So we will see in a few minutes. So I need first to introduce a few things. So let NV I make it short. It means NV is a new game. I need to introduce what is a null player. So a player, so an element I in the set of all players is a null player if for any coalition not containing I, so for any coalition which doesn't contain I, then V of S union I is equal to V of S. And I mean, it's quite understandable why it's called null player, because it means the worth of a coalition with this player is the same than without. So this player doesn't bring anything to the coalition. That's why it's a null player. The coalition doesn't get anything anymore by adding this player. Okay, so this is a null player. And there is a second notion of what are two symmetric players. So in the same definition, this was the point 1, the point 2. We consider two players, I and J, and they are called symmetric. We have already seen the notion of symmetry in a different setting. So they are called symmetric if for any coalition which doesn't contain these two players, we have that the worth of this coalition together with the player I is the same as the worth of the coalition together with the player J. So they are symmetric because to any coalition, they bring the same amount of money or the same utility. This is a notion of two symmetric players. Okay, so this is the end of the definition. I define what is a null player and what is a pair of symmetric players. And now we characterize we're going to characterize TU games based on these notions. So this is something I did about bargaining problem. The notion of efficiency. So I'm going to be careful. I'm going to use phi today always for function which associate to any TU game a point in Rn. So I don't write always this. This is an allocation rule. Whenever I use phi, it means precisely a function from the set of all TU games to Rn. So phi satisfies what is called the EFF condition. These are definitions. If the sum of phi of oh yeah. I will explain what I mean by this because for any so what do I mean by this? Remember phi associate to any game, any TU games, a vector in Rn. And the TU game is a pair. This is NV is one TU game. So phi of NV is an element in Rn, it's a vector, and I take its component I, because this vector contains information about what all players can get. Now I take the component I, it's an index I, and I sum over all I. So I take the vector and I sum the different values of the vector. And I'm saying that it's efficient if the sum of all entries of this vector is V of n. What does it mean? It means the point in Rn given by this phi of nv, its components sum up to the value or the worth of the grand coalition. Right? This is efficient. So it means really, maybe I should make it smaller. This is an index I. If you have any question, you interrupt me. Again, this is a game. I take phi, I get a vector. I sum up the contribution of these, of all entries of this vector, and I should obtain phi v of n. This is called efficient. So this is the first. In fact, it's not correct. We do not characterize TU game. I should say we characterize, sorry, it's a mistake. We characterize phi from Gn to Rn. These are characterization of such functions. It's not a characterization of a game.
Adding up the numbers in a real number.
Yeah, it's adding the different entries of a vector, because one entry represents what one player gets. So if I add the different entries, I get what all players are getting. The second characterization, it's related with null player. So I use again this word. Phi satisfies the NPP condition if whenever we have a game or any NV, a game, a TU game, and for any I null player, so I is a null player, then the phi of NV entry I is 0. So it's different because here I just look at the entry of a null player, and I'm saying that this null player should get 0. Remember, the null player doesn't contribute to anything, so the characterization here is if a null player, a null player will not get anything through this function phi. This is a rule. I'm not claiming that it's fair rule, but these are definitions. The notion of symmetry, I defined just before what are two symmetric players. So I will say that phi satisfies the SYM condition. Remember, two players which are symmetric bring the same amount to each coalition. So if we want to respect this symmetry, the phi should satisfy that for any game NV and any symmetric IJ, then what we expect, what the player I will get should be the same as what the player J will get. So phi of NV entry I is the same as phi of NV entry J. The two players bring the same to all coalitions. So we give a definition for an allocation rule or for a map from the set of all games to Rn, which respect this symmetry. It's quite natural. And the last condition, or the last definition, these are not conditions, these are definitions so far. The last one is called the additivity or the additivity property, which is more difficult to justify, but it's quite natural. The additivity phi satisfies what is called ADD, additivity condition, if for any two games. So now we have NV and NV prime. So we have two, or NW, I don't like prime, NW. If for any two games, we have the following property, phi of I'm not sure, there might be a mistake in my note. I will check. This is what should be written. I don't know if it is written this or not. What does it mean? This is a game obtained by taking the sum of two games. So what means this game? It means V plus W of any coalition is just the sum of the two values, W of S. So this condition says that if you add two games, then this rule should be additive. We need this condition. Now, is it a correct condition or not? This is just a definition. So remember, I want to give you a rule which send any game to how to distribute the utility or the money among the players. And I have defined four rules, not for rules, but for property that this phi can respect. One is called for null player, one is the symmetry, one is the addition, and the one is efficiency. And I will just change the order in my presentation. So I will give you directly the statement before giving you the characterization of this rule. So the main theorem in this section, it's about Shapley rule. There exists a unique map phi from the set of all TU games to Rn, which satisfies the four conditions I have just mentioned, which satisfy the efficiency condition, the null player condition, the symmetry condition, and the additivity condition. So and I'm going to say this phi, this unique phi, is called the Shapley value. And I'm going even to give you a characterization of formula. So how should you understand this? It means if you believe in these four properties, or if you want to impose these four properties, there is only one way to distribute the money or the utility. So if you want to respect the four conditions I mentioned, the fact that any null player should not receive anything, the fact that two players which are symmetric should receive the same thing, the fact that it's efficient, so we distribute the total worth of the grand coalition, and this additivity condition, if we want to respect these 4 rules or these 4 conditions, there is only one way to give the money for all games. So it's a quite strong result. And how, you have a question?
Does it restrict the space of game?
All these are conditions on the set of games.
But the other 3 conditions are on the players because
No. There are these 4 conditions there are properties of phi, but they use indeed they use something about players, and this one, you are right, is something more about games, but there are 4 characterizations of phi based either on properties of games or based on properties of player. I agree. But efficiency, it's not a property about players. Efficiency is the fact that we distribute the entire amount of money or the entire utility. So no, you're right. There is a small difference, but they are all characterization of phi. And what is this Shapley value? So there is even a formula. So I give you the formula right now. The Shapley value. It's a function from the set of all games, all T to Rn. And how is it given? Defined. So for any game, for any NV and any I a player by phi S of this S, it's a bit misleading. I did hesitate to keep it. This S has nothing to do with a subset of with a coalition. Okay, let me put it in red. It's a S related to the name. So this S has nothing to do with a subset of N. So this entry I, again, this is a vector. I look at the entry I of the vector. It's a sum over all S inside. So let me write the formula and we will comment on it. It's a bit complicated, but we don't need to remember this formula. I put a times because the line is not long enough. So it's multiplication by okay, this is a formula. So again, this is a vector in Rn. I take its component I, and this component I is related to the player I. It's given by a sum over, now this S is any coalition which do not contain I. So I do a sum over all possible coalitions. Let's first look at this term. This term is the worth of the coalition together with I. So we add I to the coalition minus the worth of the coalition without I. So it's, in a sense, it is what I bring to this coalition. This difference is what the player I add to the coalition S, because it is the worth of the coalition when I is inside minus the worth of the coalition when I is not inside. And we have some, so this is a difference of worth, and this is a numerical factor, and this numerical factor contains the size of the coalition factorial. I guess you have all seen this factorial. So it's an S number of element of S factorial times total number of players minus S minus 1, also factorial divided by N factorial. wait, S is always smaller than N because it contains not all players. So this difference can at least, it's 0. The minimum value is 0 and 0 factorial is 1. So no. So you should think about this as a weight. This is a number. It's a weight, but what is really important is this difference, what player I bring to the coalition S. So this is a complicated formula, but this is something that you can compute. If I give you a game, it's complicated, but this is computable. And if you compute this number and you do it for all players, then what each player will get respects these 4 conditions. And this is the only solution to this problem. So this is the only way to distribute the utility among the N players such that these 4 conditions are satisfied. So I think it's quite interesting. Okay. If we drop one condition, like the additivity, then you lose the uniqueness. So
You only consider one game.
No. It's for each game, you get a vector. And this vector is what player, or the entry I of this vector is what player I will get for this specific game. But now this formula is a formula for all games so that they satisfy these 4 conditions. So it's the same formula for all games. That's why this is an arbitrary game. But if you apply this rule, it's efficient. It gives 0 to null players. It's symmetric among players, and it satisfies this additivity condition. Now you can wonder, there is a small question, and I don't think it's unfortunate, but it's a fact. Last week, we introduced the notion of imputation, set of imputation and Kerr. It turned out that it's a remark. If the game NV is super additive, then phi of n, no, not this one, is phi s sharp, s for sharp. Phi s of NV is inside the set of imputation. So it means no player has interest of not choosing this solution, but it is not in the Kerr in general. It means sometimes it can be, but not always. And we have seen the Kerr might be empty, while this formula is never empty. I mean, it's a formula, you can always compute it. Okay. Yeah, the approach are not exactly the same. Last week with the Kerr, we looked at a solution so that no coalition would go against. But today we are more precise in the sense we really distribute the utility with one formula respecting some conditions. Is there any question or remark? I will present a second one, and in the third one, you will understand that even more, because I will present the third one is the simplest one. I could have started with the simplest one, but I will explain you why I didn't do it. Section 5.6, it's a second rule, a bit less interesting, but still we can learn something. It's called the Banach value. It's another allocation rule, so it's going to do the same. So I start this time by defining it. What is a Banach value? This time it's called phi b from the set of all TU games to Rn is defined by a bit quicker. It associates to any game entry I the following thing. So it's again a sum over all coalitions which do not contain I. So I take a coalition which doesn't contain I, and the same factor V of S union I minus V of S. So the same difference, but now the weights are much simpler. 1 over 2n minus 1. So if you look at this, it's good to have these two formulas next to each other. The second part is the same as here. The difference between what the coalition gets with the player I or without. But now we don't have these weights which are complicated. We have only a common weight or common factor, 1 over 2n plus minus 1. You can wonder, where does it come from? Why do we have n minus 1? Can you guess? Not always you, somebody else. Can we guess why we have n minus 1? Look, we are summing over all coalitions of n minus 1 players because we avoid player I. And how many of them we have? Exactly these 2 power n minus 1. So in fact, what we do, we take all coalitions which do not contain S, we do the sum of these differences and we divide by the number of terms we have taken. So it's an average over all these differences. So it's much simpler. So of course, this function phi b will not respect the same 4 conditions, but again, it will respect some conditions. So this is a definition of the Banzhaf value. And now I have to tell you which conditions are satisfied if you choose this. It's a bit artificial. Let's see. So this time I do it in the reverse order. I first set, I will give a name to something. I will give this number here. I will call it m bar I n b. It's a definition. I just call this. We will see why. It's the sum of all contributions of player I to the coalitions S. And I will set m bar of NV. Why NV? Because it's always based on one game. So it's for each game. M bar of NV is now the sum over all players of what I have just defined, m bar I. I just defined these two things. An observation. This is visible on the left. This Banzhaf value of NV entry I is simply 1 over 2 n minus 1 times this m bar I. This is just by definition of how I define it. Okay. And now the theorem about this Banzhaf value. Again, what are the properties of this allocation rule. So theorem. Phi b, phi b is the only, or the unique, is a unique allocate, the unique allocation. It's a unique allocation rule. Phi satisfying, it's satisfying three conditions: NPP, sim, and add conditions. So already three of them, and such that phi of, no. Okay, I told you it's a bit artificial. Look at this. So the three conditions are understandable. I already mentioned them before about null players, the symmetry, the additivity condition. But it's not enough in order to get uniqueness. You need one more condition. And this condition is that it's visible on the right. These bands have value satisfy that when you add the contribution, you get 1/2 power n minus 1 times this value I just introduced. But this value has been introduced after having defined the bands up. So it's a bit circular. If you think about it, I first introduced this function and the red guy and this definition. And of course, if now I sum these values, I obtain exactly this M bar. And what is written here is that precisely the bands have value satisfies this, which is not surprising because it has been constructed for that purpose. As I said, it's a bit circular. Still, we have a characterization of this allocation rule in terms of 4 conditions. However, there is a weak point for this value. It's simpler. I mean, the formula here is much simpler than the previous one, so this is a good point. A weak point is that, let me write it, the sum, so remark, we may have that the sum over I of these value NV index I. So if we sum what all players get with this rule, it's sometimes bigger than the worth of the grand coalition, which is a bit weird if you think that the worth of the grand coalition is the maximum amount of utility. This way of distribute, if we follow this rule, we may need more money than the one available. So, but still, I wanted to introduce it. Now, as I said, I'm going to give two much simpler value or simpler rules. Do you have any question? So the two simpler ones, which are probably the most used one, are called equal division values. I directly start with the definition. The first one is the equal division, or the equal division value. Phi E from the set of all games to R n is defined by, is given by, or defined. Phi n, phi E for the game NV is by definition, you take the total worth, or the worth of the grand coalition, you divide it by n, the number of players, and you give one part to everybody, the same part to everybody. So this is a simple rule. You give the same amount. You take the total amount, you divide by n, and you give it to everybody. This is called the equal division. And another one, which is an epsilon more complicated, it's called the equal surplus division. This was the equal division. Now, the other one, which is denoted by phi SE, takes any game and send it to Rn. How is it defined? Phi SE of a game, NV. Entry I. It is every player gets what they can get without playing, without interacting with the other players, plus what is called V0 of n divided by n. What is this V0? We already saw it last week. I just recall it. V0 of n, it's called the zero normalization. It's by definition, you take Vn and you subtract the contribution given to all players. And this is why it's called the surplus. What you have when you have subtracted what each player is going to get, you take this difference and you divide it by n. So I think this is understandable, is each player get what they can get without playing, and you take then the difference and you divide it by n. So these two rules are very simple. But then you can wonder, oh, for the previous one, I gave 4 characterizations. So they satisfy 4 properties. You can wonder, what about these very simple rule? What kind of properties they satisfy? And it's also interesting to look from this perspective. So let's look at the properties that either this equal division or this equal surplus division, what are the properties that they satisfy? So I reverse the order compared to the other two. The other two, I first defined the properties and then I gave, or we can look at the phi, which set the allocation rule which satisfy them. Now I first give you these 2 easy rules, and let's look at the properties. So how to define them? So it's again a characterization. of phi from Gn to Rn. The first characterization is called the nullifying. I was surprised. This has been done quite recently. I think the paper containing this definition on the proof was written only 10 years ago. So what is a nullifying player? So, no, sorry, oh, no, I've missed one paragraph. I first need to define what is a nullifying player. So first I need to characterize, the definition. I consider game NV and a nullifying player I is a player. Okay, the sentence is not good. I is a player such that for any S inside the set, for any coalition with I inside S, V of S is 0. So it's the worst player in the sense that whenever this player is inside the coalition gets 0. This is why it's called nullifying. So don't take this player with you in a coalition because it means the coalition will not get anything. So this is the definition again. It's called a nullifying player. Whenever a coalition contains this player, the worst of the coalition is 0. And the second one, the player I is called domifying player. So if for any S coalition containing this player, the worst of the coalition is nothing but the sum of the individual contribution. It's a bit different. Here it says if J is in this coalition, the fact of being together doesn't give you anything. The worst of the coalition is just the sum of the individual contributions. So I have introduced what's a nullifying player and a domifying player. And now I can characterize allocation rule with these two terms. So this is the end of the definition, but now characterization. Of phi from so the first one is called, or is related to the nullifying player. Phi, that is phi there. It's called NULG condition. If for any player which is nullifying, how much money are you going to give to a nullifying player? If whenever this player is in a coalition, the coalition has 0, so probably phi of NV entry I is going to be 0. Which is quite reasonable if whenever this guy is in a coalition, the coalition was 0, the rule should give 0 to this player. And the same, you can already guess on the second one is called the dumbifying player. It's related to dumbifying player. So phi satisfies. Now the name is du mg. If for any I which is dumbifying, remember it means that whenever this player is in a coalition, the worth of the coalition is just the sum of each independent player. So satisfy this, if whenever you have a player which is dumbifying, then phi of n v entry I, the only thing you can expect is that this player will get v of I. You cannot expect more because whenever he is in a coalition, the coalition gets us this number. It doesn't say anything about the other player. It's dealing with either nullifying player or dumbifying player. So this is quite natural. And now, what is the theorem? So remember, I wanted to characterize what is the equal division or the equal surplus division. And I'm going to do it with these two characterizations I put there. So the theorem is that phi is, so the first one is a unique allocation rule satisfying. So it's efficient. It is NULG. It is symmetric. And it is additive. So the only difference with respect to what I introduced before is this new condition. And the same characterization for the surplus as phi SE is a unique allocation rule. That is fine. EFF. DU, the last one I introduced, DUMG, symmetry and additivity. So whenever you play a game and you just distribute the same value among all players, then very proudly you can say, oh, we are respecting these 4 rules, and this is a unique way to respect these 4 rules. Or if you first give to each player what they get without playing, and then you divide the rest by n, you can say, oh, we are satisfying these 4 rules. And this is a unique way to satisfy these 4 rules. Okay? Is there any question or remark?
Find the NPP rule, is that different from nullifying play? Because that's also like null player.
No, it's different. A null player is a player which doesn't bring anything. A nullifying is worse. Whenever you have such a player, the coalition gets 0. So not only this player, but the entire coalition gets 0.
But all nullifying players are necessarily null players, right?
That's probably true.
So then it would be satisfying with every condition at the same time.
Again, these 4 conditions are necessary and sufficient. So if you replace by something else, you have the same statement. But yeah, null player doesn't bring anything. A nullifying player make that nobody get anything in the coalition. Okay. So today up to now, we have seen 4 ways of distributing the utility or the money, and each of them satisfy 4 properties, and it's completely defined by these 4 properties, because in the statement it says it's unique. So if you give me these 4 properties and you say we have to respect these 4 properties, I have to take this phi. The other one wouldn't satisfy these 4 properties. So it's a uniqueness. All right. Still, there is one thing which you can be unhappy with. There is no relation between, almost no relation between what I've presented here and the notion of Kerr that we have introduced last week. These point, these, is it still somewhere? Okay. When we take one of these application rules, it gives us a point in Rn. We can wonder, and it would be natural that this point is inside the curve. But unfortunately, it's not true because we are not dealing exactly with the same approach. So I want to introduce one more thing where we are inside the curve. So one more allocation rule, which has an image inside the curve. And please be aware that the curve sometimes doesn't exist. So the question is not well posed in general. But if the curve exists, you can wonder if you are inside. So this is section 5.8. It's called nucleolus. So we want to have an allocation rule belonging to the curve whenever this one is not empty. You have a question? Okay. It's yes, but in French, this is the word, and it's this is a curve.
Well, it's fine. We appreciate it. We appreciate
it. This is multiculturalism. Okay, okay, whatever you want, use one of them. You need one of them for sure. Okay. Now we move to something else. Okay. It's a bit more involved, but the good point, as I said, is that it's inside this. Okay, so I need to explain what is this nucleolus. Okay, so we consider one game. A TU game. And I fix any point in Rn, any allocation. And then I set E of Sx. I give a definition. It is V of S minus this sum. Okay, so It's a definition. It's a difference between two numbers. The worth of the coalition S minus X is arbitrary. X is arbitrary. I subtract the sum of its component in S. And remark, if X is in the imputation set, you need to remember what is the definition, then this E of n x is 0. Because by definition of the imputation set, the set of the sum of these guys is equal to V of n. It's efficient. But I'm claiming this just for the nx, not for any other things. And we say that this E of Sx is set to measure the dissatisfaction, the degree of dissatisfaction of S, the coalition S, with respect to X. And we will see why. The dissatisfaction of S with respect to X, and why we interpreted it like this. Indeed, if X is in the core, now I'm scared whenever I pronounce this word. This is, okay. If X is in the core, then, so what is the can you tell me the sign of this? If X is in the core, you have to look back at the definition of the core, but it turned out that if X is inside, then this number is negative. And remember, the core is something good because no coalition wants to get or to escape from any point in the core. So if this is negative, I mean, if we are in the core, it's negative. If it is positive, it means that we are not inside, and that's why it's called to, it's said to compute the dissatisfaction. Okay. But this vector, this quantity is going to be important. So far, it's only a definition. I started with one game, 1 point, and I define a quantity which is just a real number. This difference is just a real number. But look, we have such a real number for any coalition. I fix X is fixed. So for any coalition, I have such a real number. So I'm going to make a vector. Set theta of X. It's going to be a vector in R 2 power n. Why? Because we have 2 power n. Yeah, it's probably better small n and not a capital N. I don't know in the notes, did I put capital or small n? Can anybody check if I put small n or capital N? Okay, so I will change it to small n. I will correct it in the new version. It's better. So it's a very long vector because remember, we have 2 power n coalitions, and I'm just creating 2 power n's real numbers. So I'm going to set theta x, it's a vector in R power 2n, with entries E of Sx. Now, in which order should I put them? Because the S is not, I mean, the set of, take a set of 4 points. Let's say this is 4. How many subsets you can easily compute, but how to order this subset is not easy. For example, how do you compare this subset or this subset or this subset? It's difficult to give an order. We can count them, but saying which one is the first, second, third, and so on, it's more difficult. There is a way, but. So I'm going to put these 2 power n numbers with put in what is called non-increasing, I hate this word, non-increasing order. What does it mean? It means decreasing. Non-increasing, but no, there is a small difference. Non-increasing means if you have 2 times the same, you can have 2 times the same, while increasing, it's ambiguous. No, decrease, sorry. Non-increasing is the same as decreasing. But yeah, you have a notion of strict or non-strict. And here, it can be that for 2 coalitions, you get the same number. So you might have the same, more than once the same number. But you start with the biggest one and you go down. So that your vectors start with the biggest number and go to the smallest one, which can be negative. Smallest one, it can go below 0. So for each x, we create one vector in R2n, and this vector is made of these numbers, but these vectors start with the biggest value up to the smallest one. And think about it, you are measuring the dissatisfaction, so you put the biggest dissatisfaction on the top, and then you go down. And it turned out that we have an order on these vectors, which is the lexicographic order. So I'm going to recall it. We use the lexicographic order. So what does it mean? I'm going to say that the vector theta y is bigger than theta of x, and I put a small l for lexicographic. So we say that theta y is bigger than theta x if, so remember, these are vectors in R power 2n, so we have 2n entries. If there exists a k inside the set 1 up to 2n, such that theta of y entry j is equal to theta of x entry j for any j strictly smaller than k, and theta of y index k. So what does it mean? Look, it means the first k minus 1 entries of these vectors are the same. And so the entry j of theta y is the same as the entry j of theta x for all entries up to the k1, not k. And at k, it's bigger. This is called the lexicographic order. So you can test what it means in R3, for example, compare 2 vectors with this lexicographic order. It's something which is very useful. It's a way to compare vectors in Rn or R2n. And if I define a strictly bigger, we also need to define theta of y bigger or equal with this lexicographic order than theta of x if either theta of y is strictly bigger than theta of x, or they are equal. Theta of y is equal to theta of x, which means all entries are the same.
Not order of S.
No?
Not
What?
increasing order of magnitude of S, right?
I mean, we have 2n numbers like this, and we put the biggest one on the top, first entry, then the one below is already a bit smaller. We can have equalities.
Values of the entries with the.
I have E, let's say, entry subset. And I take a second one, 1, 2, x. Okay, so I have these two. Let's say this one is 1, this one is 1.5. Then I'm going to put the first entry of the vector is this one, the second entry is this one, and then I continue. I mean, if the other.
One, then 1.5.
I said non-increasing means decreasing. The first entry is the biggest one, second entry is slightly smaller, and so on. But I could have another one, and then I just put in arbitrary order. It doesn't matter.
That's like a comparing thing in lexicographic order. Does it even make sense?
Please think a second before you ask questions. You cannot ask 100 questions every lecture. Okay, so I define an order on these vectors. And now the main definition for this section is what is the nucleolus. So let N be a game. And I assume that its imputation set is not empty. If its imputation set is empty, the following definition doesn't hold. It doesn't exist. Then the nucleolus is the only y in I of v such that theta of y So this is not clear. This definition is, you need to prove something for this definition. What is, you can compare, for any point, you can construct these vectors and compare them. What is not clear is that there is only one which is bigger than all the other one. So there is a lemma, I'm not presenting it, but there is a lemma before this which shows that inside this set of imputation, if you use this lexicographic order on this theta of any point, you have only one which is bigger than all the other one. It's not automatic, if you think about it. It's not for free. But it turns out that this result is true. There is only one, and we call it this nucleolus. And why is it interesting? Because now we have remember last time I introduced this imputation set, and inside I introduced the curve. And I mean, we have no way to distinguish until now. We had no way to distinguish the point in this set. You have points, but they're all not all the same, but there is no way to say which one is better than the other one. Now, suddenly, we have one characterization. We have one and only one, which is bigger in a certain sense than all the other one. And the main result in this setting I can state it, okay, as a theorem or lemma, it doesn't matter. If the core is not empty, then, oh, I didn't give an, okay, I should write a notation. The nucleolus, I should call it eta of V. So it's a eta of V, I call the nucleolus eta of V. So then this eta of V, so it's, if you think about it, this is just an element of Rn, but inside the core, inside the imputation set, sorry. But the statement is if the core is not empty, then this special value is inside C of V. So what does it mean? It means we have now a way. I did this picture at the beginning. I said, okay, suppose this is I of V, then inside, oh no, I mentioned before that they do not look like this. They are polytope. So they look like this. Their faces are made of planes. So this is I of V. And inside I of V, I have, let's say, this, which is C of V. They have this shape, not the one I did before. And now we have one way to distinguish a special point inside, which, if you remember, I said these entries represent the dissatisfaction. So we are minimizing the dissatisfaction. So then this point, this is eta of V, is inside the core and represent the minimal dissatisfaction. For all coalitions. So I wanted to present this because compared to last week now, we have one specific point inside the core. The core is already a good because no coalition would go against any point inside the core. But now we have one specific point inside which has one additional property. So if we play this game, probably we should choose, I mean, this is a new allocation rule, is to take this point, but there is a condition. And this is not true for all games. So I cannot say that it is an allocation rule as the one I introduced before, because the one I introduced before were true for all games. Now this is true for, I mean, this is meaningful for games with non-empty core. But by the way, last week we have seen if and only if for this. It was if the game is balanced. So for balanced game, this is interesting. Okay, do you have any question or remark?
Imputation is already lexicographically ordered. That's why we can take the lexicographic ordering of theta, right?
You know, Rn, you have any Rn, you can put the lexicographic order. But now we are not putting the lexicographic order on Rn. We are putting the lexicographic order on R2n. Because this is what we get when we consider these vectors theta. That's it. Okay, I have not really the time to start the new section, which is the last one for this chapter. Let me just tell you what it is about, because I find it's interesting. So far, all players could speak to all players. That's why coalitions, you could generate any coalition. I didn't put any restriction. I just consider a coalition inside, or all coalitions inside. Now, what happens if not all players can speak to each other? If inside N, some players can speak to others, but not to all of them. How do you encode this information? And the way you can encode it is with graphs. And I'm happy because we have already introduced the notion of graphs at the beginning of chapter 3, probably, or 2. So a graph of N players. So it's going to be N points, and I will use the same way of giving a name. So at least N players. And I can represent communication by edges. So let's say these three can communicate. Okay, this is a possible graph. It's a simple graph in the sense that I don't put double edges. I don't consider loops. And I don't put any orientation. This can be used for other purpose, but not for this purpose. So it means if I consider this graph, only these points can speak, this one can speak, and this one can speak. No, he cannot speak. So this is a way to encode one additional information, which is a restriction. I'm restricting compared to before because I impose some kind of boundary. So not all coalitions will be possible because, I mean, if they cannot speak, they cannot generate a coalition. Yes?
Why is the notion of a graph instead of a partnership if there's no sense of distance?
You are right. I can probably use partition. Yes, it would be the same. Yeah. All right. Yeah. Probably it would not make things very different. I mean, it's just the word we use. You are right. I could use partition. We partition. No. You know, I still want to, at some point, I still want to introduce all S in N. And if I partition, I have a problem. What is S? So I'm contradicting myself, but you will see next time. I still need to consider all subsets. So at one point, I need to consider this subset for a certain definition because games, you remember a game, TU game is NV, and V is defined on all coalitions. So if I want to keep the same definition, I need V to be defined on all S, even if some S will not be realizable. I will not be able to, because they don't speak to each other. So this is not a connected, we will see this notion. It will not be a connected coalition, but I still need to define V on all S. If I use the notion of partition, probably I cannot do it anymore. But yeah, it's just some definition. Yes?
Would these be, in this context, meaningfully different if you, for example, connected one to 6?
I'm not sure I understand.
Like, is one considered able to communicate with 6 because it's going through someone? Or would it be different if you had connected 1 and 6 directly?
So yeah, this vertices can communicate. They cannot communicate to this one. You will see how I use this next week. I just wanted to, maybe you can read the notes or just wait until next week. So yeah, next week we will finish this and this section, and probably I will give some examples, some applications next week. Okay, so thank you.